I hope everyone's doing well. I am Mr. Ish. Thank you for joining me for this interesting video where we're streamlining and shortcutting our way through this lateral surface area concept, which many students find rather confusing when they go through the formalized process. But here I'm showing you the line, the band, the integrate technique. I call it the LBI. It makes the lateral surface areas very easy in terms of determination. We will look here at the cylinder and we will look at the cone. You know what a lateral surface area is. It does not necessarily imply the entire total surface area, but only the lateral surface is being examined. When you're looking here for a cylinder, you can start with an x and y axis, and we can look at everything along the x-axis in terms of a height, h comma 0, and we can look, and we can call this right here x is equal to h. We can look here along this dimension, y is equal to r, and that would be my radius. If you were to look at this function right here, or this segment, and rotate it around the x-axis, you know you're going to develop a cylinder. When we're talking about the lateral surface area, we're not talking about these circles here on the side. We're only looking at the lateral surface, and that's what we're looking at. But what is the line, the band, the integrate? If I were to take a little slice and pluck it out, I have this. If I were to cut it and I stretch it out, I have a line. This line, the length of this line is equal to the circumference, and you know that it's kind of like a circumference because it came from a circle. We cut it, we stretch it out, we have a circumference, hence it's a line. What's the formula for the circumference? 2 pi r. But I need to know what the radius is. What's the radius? The radius is always the distance from your line of rotation, here the x-axis, to your function, and here the function is y equals r. So hence the radius is equal to r, my circumference is equal to 2 pi r. Now I have to convert this into a band. What's a band? You're giving this line a certain sense of width. That's what you're doing. So you're no longer looking at a line, but you're looking at a width. And you're going to get that width by doing a dy or dx, a derivative, and you're going to square it, and then you're going to add it to 1, and you'll do the square root. You have to do this procedure because our formula will be this. You're doing an integral from a lower limit, upper limit. You're doing a line, and you're incorporating in a certain band, and you're incorporating your dx, your integral with respect to dx. But look over here. I have a circumference 2 pi r, I have a lower limit 0 and an upper limit h. My integral is 0 to h. My line is giving me a 2 pi r, so I'll put that 2 pi r. Now I need to bring in my band by this formula. If y is equal to r, which is your function, then dy over dx is equal to the derivative of r, which is a constant, it's a 0. You're looking here at square root of 1 plus 0 squared, which is equal to a 1. And you're multiplying by 1, and then dx. This right here represents your lateral surface integral for a cylinder. When you integrate it, all of this can come out. You have a 2 pi r 0 to h dx. You have a 2 pi r x as your antiderivative and h in a 0, and you know your end result here is a 2 pi r h, which represents the lateral surface area of a cylinder. Again, the LBI technique. You determine what your line is, which is your circumference. You give it a certain thickness, we'll call it a band, and you bring in this formula right here by bringing in the derivative squared plus 1 in a root. You combine all of this and you integrate, hence the LBI technique. We'll end now with the lateral surface area for right circular cone determination. Right circular cone, lateral surface area is easy. 0 comma 0, and you're looking at a certain segment rotated on the x-axis. I'm looking over here at something which is an x is equal to h. I've come here as high as y is equal to r, your radius. When you do the rotation, you're developing a right circular cone. That's what I have. Again, the lateral surface area is not going to incorporate the area of this circle. Just like as the cylinder, the side two circles aren't being incorporated. You're only looking at the lateral surface area. If you eliminate the circle here on the side, when you open it all out, you're looking at a item which looks like this. You're looking at the surface area of that. When you wrap it around, you get your lateral surface of that cone. Anyhow, let's bring everything into play. I make a little cross section and I bring it out. It looks like a circle and it has a certain radius. What's this radius? The radius is equal to the distance from your line of rotation to that function. What's the function? I have a point here h comma r. I have a point here 0 comma 0. I have a slope y2 minus y1 divided by x2 minus x1 r over h. I have a certain line, y is equal to mx plus b, but there is no y-intercept other than the origin. It will be rx over h. This right here represents my radius, distance from your line of rotation to your function, rx over h. That's what it is. But I have to bring it into a form of a line. When you cut it open, you're determining a certain circumference, and you can do that 2 pi r. 2 pi rx over h. That's my circumference, 2 pi rx over h. I'll save this. I have it. We don't need to have this anymore. I'll bring it right over here. Y was equal to Rx over H. Now I have to give it a certain band, make it into a band, and I will do that by doing a dy over dx is equal to the derivative of this. It'll be R over H, and then you'll do 1 plus dy over dx whole square, which is R over H whole square. You can do this. You'll have square root of H square plus R square over H square. When you do the algebra, the fraction algebra, you'll have square root of H square plus R square over H. This is what I have. These are the two items which are coming right over here. Your line, which is your circumference, and your band, and you're integrating it. So let's integrate it. What's our integral? From 0 up to the higher limit, which is H. 0 to H. We have certain items here which are constants, 2 pi R and H. Let's bring it 2 pi R over H. Over here I have a constant 2. Everything here is a constant times H square plus R square and a root divided by H. What's the only variable? This. X is the only variable. X dx. Combine all of these. I have here a 2 pi R square root H square plus R square divided by H times H, which is H square, times the antiderivative, which here will be X square over 2 with an H and a 0. When you compute this antiderivative, H is coming in, you'll have a H square over 2 times H square over 2. This cancels out with this cancels out with this. The only thing which remains is your lateral surface area, which is pi R times square root of H square plus R square. The lateral surface area for right circular cone is this, and it should be right, and we've done it. Remember the line, the band, the integration technique, LBI. Determine your line, give it its circumference formula, run it through, give it a certain width, and run it through by means of the derivative into this formula. As you know, I'll put it here again, 1 plus dy over dx whole square all in a root. This right here gives you your band. Everything else is the normal integration procedure you're familiar with, and that's it. Thank you for watching.